Hi, good afternoon, and now I want to start with chapter 19. Here we are talking about electric potential. The potential, it is an idea that is really very similar to the idea of pressure. Here I have, let's say, parallel plate, and of course I have an electric field that is gonna be like uniform like this. And if I have a positive charge, we are going to see that there is gonna be a potential energy related to this charge, and I can calculate the work to make it like move from one place to another here using the work function, and that work function is negative, the change in the potential energy. And then I can say also that this is going to be the potential energy final minus the potential energy initial, and I'm going to get a negative here. The potential energy, the electric one, we are really calculating it based on the product of charge in coulombs multiplied by the electric potential, and this is in volts. Electric potential energy, it will be calculated in joules. We're going to define something called electric potential, or like what we usually use for this one, we're going to say voltage, and that is the potential energy per unit charge. Then it equals the potential energy divided by Q. Voltage difference can be calculated as VB minus VA, okay, and that is delta, the change in the potential energy divided by Q. 1 volt equal 1 joule per Kelvin. Now we can answer this simple question here by saying how many electrons move through a headlight each second when a 12-volt car battery runs a single 30-watt headlight. How many electrons pass through it each second? We can say that we need to calculate the charge, and then it's going to be the change in the potential energy equals Q times the change in the voltage, and that is going to be negative 30 divided by 12. I need to find what is really the energy, and that is going to be the power times time, and therefore in every second is going to be 30 joules. And then using this equation, I will be able to calculate the Q. Now the number of electrons, remember, we did this in the previous chapter. Q equals NE, and therefore uppercase N, which is the number of electron, equals Q divided by E, and that is going to be 1.56 10 to the 19 electrons. Many times it's more convenient to use other units than, I will say, joules, and we can use the 1 electron volt as a unit of energy. And that is 1 electron volt is 1.60 10 to the negative 19 joules. Okay, then this is really the electronic charge. Now let's talk about now conservation of energy. We know that we have that in physics 120, and maybe we said here this is the, I will say, potential energy, and that is kinetic. Then we can say the total equals the total at the final point. And here let me assume that I have here a charge that is plus, and I have a plus charge that is going to be at rest at this point, then ki is 0, and I will be able to calculate its potential energy based on what is really the distance here. And I can also calculate what is really gonna be the final when I will, bring it, um, in moving in this direction. Then, sorry, no, here I wanna have, if I wanna have it like here at infinity. Therefore, I'm gonna move it this way. Yeah, I'm gonna move it away. Then I know that then the potential energy final at this point is gonna be 0, and then K final is gonna be calculated based on this equation here. Q times V should equals 1/2 mv squared. Then the potential energy that we have initially here should equal the final kinetic energy, and then we will be able to find what is the speed of this. We need also to find the relation between electric field E and the electric potential voltage, and this is the relation. The voltage, if we have a uniform electric field, is going to be E times D. E is the electric field. Okay, here E can be calculated as VAB over D, and 1 Newton per Coulomb equals 1 volts per meter. These are the two units that we use for the electric field. Let me solve this question. An evacuated tube uses an accelerating voltage of 40 kilovolts to accelerate electrons to hit a copper plate and produce X-rays. What would be the maximum speed of these electrons? Here, again, the potential energy, it is E times V, and we know that the final, this is I, and that is final. And then we can put them equal to each other, and from that the velocity can be calculated as the square root of E 2 times E times voltage divided by M. Here E, it is the electronic charge, which is 1.6 10 to the negative 19, and M is the mass of the electron. This is applying the second equation. What is the strength of the electric field between two parallel conducting plates separated by 1 centimeter and having a potential difference voltage between them 1.5 10 to the 4? We know that VAB equals E times D, then E, it is the voltage divided by distance. Remember that distance should be in meters, and because here it is in centimeters, we divide it by 100 to change it into meters. Thank you, and I will continue working on the chapter. Thank you.